catalyst and reagent. We are going to discuss heterogeneous catalyst. The reactions in which reactant and catalyst are in different phases, okay, are known as heterogeneous catalysis reaction. First of that, we are going to discuss is Rene nickel. It is developed by Murray Rene in 1926, okay, and it was used for hydrogenation of vegetable oils. The Rene nickel is a spongy material, gray or blackish in color, and it is pyrophoric in nature. So most of the time, it is stored as air stable slurries. It is prepared by boiling a nickel aluminum alloy in alkaline medium. NaOH is used, and when this nickel aluminum alloy is boiled in NaOH, the reaction can be written like this. We'll be getting Rene nickel, okay, formation of this. Now, as we can see, we require strong alkali medium for this preparation. Okay. So, care has to be taken while using this Rene nickel. If the reactant or the compounds are susceptible for these actions of alkali, we cannot use Rene nickel, okay, in those conversions. After the reaction, if you want to deactivate the Rane nickel, it is treated with acid and then it is deactivated and stored. Next is reactivity of reactions of Rane nickel. It is used for hydrogenation of polyphenic double bonds. A reaction can be represented like this simple reaction where we have styrene. It is reduced to this ethyl benzene. Okay. This reaction is smooth reaction and occurred at room temperature. Okay. If Rane nickel is used for the hydrogenation of aromatic ring, or we can also say reduction of aromatic ring to non-aromatic ring, then the reaction has to be carried out at higher pressure and temperature condition. For example, this methyl ester of benzoic acid or methyl benzoate, if we want to reduce the benzene ring in this structure, okay, we require higher pressure, 100 atmospheric pressure, and the reaction is usually carried out at 60 degree to 70 degrees Celsius, and we get this reduction of this benzene ring to cyclohexane. Rane nickel is also used for hydrogenation of nitriles. The nitriles or cyanides get reduced to primary amines. So here, the cyanide is reduced using Rane nickel at room temperature to the CH2NH2, primary amine. Next is hydrogenation of nitro group. The nitro group readily get hydrogenated to the amine group. So, nitrobenzene reduced by Rane nickel. The requirement for the reactions are pressure at 70 atmospheric and temperature around 70 degrees Celsius gives aniline as the product. Next, we are going to discuss Adams catalyst, that is platinum oxide. Platinum, when it is in its oxide form, P2O2, it is known as Adams catalyst. It is also known as platinum black. This platinum oxide get reduced to the metallic platinum by hydrogen in the reaction mixture. So what happened? In situ, the platinum oxide it get reduced to the metallic platinum. okay, in presence of hydrogen. The hydrogen get added to the unsaturated compound in a syn manner. So we can say syn addition of hydrogen is observed. Let's see some example. First, reduction of olefinic double bonds, simple olefin without conjugation. So we have this substituted cyclohexene, which undergo reduction in presence of platinum oxide and gives a 1,2-dimethyl cyclohexane. Here, the stereochemistry is shown to represent the syn addition of hydrogen. Both the hydrogen are added from the same side of the double bond. Reduction of aromatic ring. The aromatic ring to which electron donating groups are attached, like OH, NH2, OR, can easily be reduced to the corresponding cyclohexane using Adams catalyst. The reaction is carried out in acidic medium, and acetic acid is added to catalyze this reaction or to speed up this conversion. So here, phenol is converted into cyclohexanol. Next, use of platinum oxide for reduction of nitriles. Here, the nitriles get reduced to the primary amine. So it is depicted in this example. You can see the nitrile CN here get reduced to CH2, NH2. Platinum oxide also reduces nitro group into amino groups, while the other carbonyl functionalities remains intact in this reduction process. So in nitrobenzene or substituted nitrobenzene is reduced to substituted aniline, okay, without affecting the carbonyl double bond. Next, we are going to discuss use of palladium for hydrogenation or reduction reactions. Palladium mostly used in the fine deposit form on an inert surface, okay, and it is used for the different reduction reactions. The inert surfaces use like carbon, calcium carbonate, barium sulfate, etc. The reactivity of this palladium catalyst depends on two things. First is the inert surface, which is used to support the palladium metal, and second is the solvent used in the reaction. So polarity of solvent also affect the reactivity of this palladium catalyst. Now, use of palladium in the Rosenmund reduction is the first reaction which we are going to discuss here. Reduction of acyl halides into aldehydes using palladium supported on barium sulfate is known as Rosenmund reduction. The general reaction the catalyst is supported by barium sulfate, okay, and it also deactivates the catalyst so as the aldehydes cannot be further reduced to alcohols. This is the general representation of a reaction. An acyl halide treated with this palladium supported on barium sulfate in presence of hydrogen, we get aldehyde as a product. Okay. So this conversion is known as Rosenmund reduction. And the barium sulfate deactivates the catalyst so that this aldehyde cannot be further reduced into alcohol. And the next is few examples of Rosenmund reduction. Okay. Here, the aromatic ring is attached to an electron donating group like methoxy group, which facilitate the reduction of this acid chloride into corresponding aromatic aldehyde. Rosenmund reduction also shows chemoselectivity. Here, if we have the acid chloride of cinnamic acid is taken, then Rosenmund reduction gives cinnamaldehyde as a product. The reduction of carbon-carbon double bond is not observed at all. So we can say this is a selective conversion of acyl halides into corresponding aldehydes. Next, the palladium is used for the selective reduction of alkynes in the form of Linder's catalyst. The partial reduction of non-terminal alkynes into cis-alkene is carried out using this Linder's catalyst. The catalyst is deactivated by lead acetate or quinoline. Here, the reaction is represented when 2-butene is partially reduced to cis-2-butene. Both the hydrogens are added from the same side and we get cis-alkene selectively as a product. The addition of lead acetate or quinoline deactivates this catalyst so that the cis-2-butene will not further reduce into alkane. This is how the Linder's catalyst is used for conversion of alkynes into cis-alkene.